Yeah, yes, good morning. I think now you can get me, eh?
Yes.
Good morning, yes, you can.
And you can see what I'm sharing, isn't it? You can see what I'm sharing, FFT
Yes, we
algorithms?
Yes.
Ah, very good, very good. Yeah, sorry, I had a problem with my laptop, so I started using a Mac, and Mac, everything is upside down. But I hope now we'll be okay. Um, so we are going to look at FFT algorithms. And as I said before, FFT algorithm just means fast Fourier transforms, and what it actually means is just a method or an algorithm of doing DFT. Yeah, already we know how important the DFT is, so that's why FFT is very important, because DFT in the conventional way, especially with long sequences, can take a very long time. But with FFT, you can cut down time in the order of thousands or millions. So the specific FFT we are going to look at is one of the two radix, two FFT algorithms. Radix 2 just means base 2. Radix FFT algorithms. And we are going specifically to look at decimation in time, because it means you are actually chopping the samples into two in the time domain. That's why we call it decimation in time. The DIF would be working in the frequency domain. The two, DIT and DIF, have the same complexity, but we're only going to look at this DIT. As I said before, it was proposed by Cooley and Tukey in 1965. So let's look at how it works, what it actually is. So from the definition of algorithm, I mean DFT, x of k is a summation of from n to of n is equal to 0 to n minus 1, x of n, e to the minus 2 pi kn over n. And that's like we have seen before. I've seen that let me see where I can be able to write with this. Yeah, I can. It looks like I can. Looks like I might not be able to write with this. That will be another. So let's just continue. So that is the definition, but we are aware that I forgot when I can't write that you e minus 2 to the pi over capital N for a particular length of samples. When you are working a particular DFT, then n is that will be a constant. The only varying variables is k and n, k and small n. So I think from DFT, maybe I just have to display the DFT here also, so that we can be able to compare the two. I think since I can't write on this one, let me open the DFT so that I hope I don't have to change the window. I think you can still see, I don't have to change to share again. I think you can see DFT. I think what we are saying, we are going to apply the same, this, why is it? Even the mouse is going up with it. Oh, that's too okay. Like Americans want to do things always the opposite. Even my mouse is moving opposite. I'm looking for WN. Yeah, it should be at the beginning. There. Really struggling with this. Forget it. Navigating this. Well, I think we know what you're talking about. That WN, we can, so we can write this as simply x of n, w to the power wn, w sub n to the power, to the power of kn. Yeah. So what we are going to do for if you use the conventional FFT, DFT, it means, sorry, when you see moving like that is because this mouse, sometimes I'm used to moving the other way around. So for each k, you have n complex multiplication because you are multiplying this e to the minus 2 pi kn, and even the signal itself will be complex. So you are having n complex multiplication because for each k, n goes from 0 to n minus 1. So that is n complex multiplications. And then, of course, when you're adding n times, then you have n minus 1 additions. Yeah. If you're adding 3 numbers, then you have got 2 additions. If you're adding 4 numbers, you have 3 additions. So since you are adding for each x of k, you are adding the x of n to multiply by this w n to the kn. Then, of course, you have n. You have to go from k is equal to 0 to n minus 1. So you have n complex multiplications, and then you have to do that n times. Yeah. So with that, you find that you have got n squared complex multiplications and n into n minus 1 complex additions. But for the purposes of complexity, we will look at the additions. The multiplications. These are the ones that bring the complexity. Those are the ones that So the complexity of obviously the highest would be the O n squared. We just look at the multiplication, so we don't look at the addition. Addition is also n squared, but mainly is the multiplication. And we are going to see that first Fourier transform, this DIT, reduces the complexity to the order n log 2n. So we are going to see that at least we are going to use, for this particular case, we are going to use periodicity in n and k. That is what we are going to use a lot as we are trying to. So here x of k is equal to n is equal to 0 to n minus 1, x of n, that. So we say we can replace this, it's actually here. Wn is equal to e to the j 2 pi over n. So this is what we're saying. I don't think we are going to use complex conjugate symmetry as such, but we are going to use periodicity in n and k, where Wn, because the period is n, so Wn to the kn is the same as Wn to k into n plus capital N plus small n. So decimation means you split xn into two sequences of length n by 2. So it means if you are dealing with 16 samples, then n by 2 will mean you are going to do with 8. If you are dealing with 1024, it means you're going to do with 512. So whatever n is, you start first of all decimating, and then recursively doing so as your sequences grow smaller. So what we are going to do, we are going to split into two sequences, one with the odd samples and the other one with the even samples. Yeah, one with odd samples and the other one with even samples. Let's see here. So for the even samples, the even indexed, we are going to have x1 of n is equal to x into 2n. I think actually we have used n and not m. Yeah, actually we have used m. So we are going to use m, so that we don't have confusion using n and m. So am I going the wrong way? I think. Yeah, that is the start. Yeah, I think this is where we are. So x of k can be split into two. So what we have the DFTs of two sequences, one with the odd samples. By odd samples, we mean the samples forgive me, I'm so used to writing that I'm so uncomfortable when I can't write. Marks. I think this particular PDF doesn't have the writing facility. Okay, so we proceed. So you can separate into two. By even, we mean the samples. I think we should have a sample somewhere. this is not a good, this is not a good one. I mean, everything is 1. We are saying this is n is equal to 0. Yeah, the index n is equal to 0, 1, 2, 3, 4, 5, 6, 7. So by odd, by even, we mean the 0th sample, we take this to be odd, I mean even, sorry, and the 2nd sample, the 4th sample, and the 6th sample. And the odd means this 1st sample, 3rd sample, 5th sample, and 7th sample. That's exactly what we mean. There we are. So for the even, we have x of 2 to the m, wk, wn, k2 to even and odd. So we have just changed from n to m, and then we are having n over 2 minus 1 samples. This is n over 2 minus 1 samples. Half of those samples, because half means you're going from 0 to n minus over 2 minus 1 instead of 0 to n. Yeah. So somebody is trying to come in. And then for the odd samples, we have the same 0 to m is equal to 0 to n over 2 minus 1, x of m 2m plus 1, wn k 2m plus 1. So these are this is the DFT of the even samples, and this is the DFT of the odd samples. Now, incidentally, I hope you understand without me writing it down. This is the same as this. How do I show you this? Well, I can't use it. Okay, if you go to, I think I have, let me go to this. It's awkward when you can't write, but we'll make it. If you square this, if you have wn squared, it means you can actually, that square, you can bring the n, you can bring that 2 here, so this becomes n over 2. So this becomes j2 pi over n over 2. Yeah, and of course, if you have n over 2, that becomes wn over 2. Does it make sense to everybody? Yeah. If you square this, you'd get w of n over 2, because that squared, we just you can take it down here, so it becomes n over 2. So that becomes wn over 2. Yeah. So let's go back where you are. That's what you're saying. This squared is simply this squared, if you consider what wn is. Yeah. So that is equal to this. So what we are doing is, from here, we are simply removing these 2. So this becomes wn squared times wn km to the power of km. So that wn squared becomes wn over 2. That's what we're doing. And the same case here. But here you can see this is Wn to the power of 2 km multiplied by Wn to the power of k. Yeah, that's what this k means. Yeah, because this is 2 km plus k, which is simply like multiplying Wn to the 2m times Wn to the k. So you can bring the Wn to the k outside. Yeah. Yeah. Are we together? Is everybody following? Omolo, are you following? Omolo Alphonse. You know, I'll be specific. Okay, thank you very much. I'm so sorry. This PDF, I can't write on it, and normally easiest way to explain when you are writing. But let's hope that we'll be able to. Let me just go back to the. Sometimes by going back is, as I said, this mouse goes the other way around. Where were we? Where did we have? No, I'm going ahead. So I think we were. Oh, here. This is Wn. So Wn is e to the power of j 2 pi divided by n. Yeah, divided by n. Now, if you square this, it means you're squaring this. But if you square this 2 which is here, the square, is simply, you can put it under n. Yeah? Like if you're dividing something by a half, it's like multiplying by 2. Yeah? Or if you're multiplying by 2, it's like, you're dividing by a half. Yes. So if you're multiplying this by 2, because when you power, it means you are actually multiplying this by 2. So multiplying this by 2 is actually the same as just dividing this by a half. So you divide this by n over 2. Yeah. I don't know whether that explanation makes sense. So it means if you square Wn, it simply becomes W of n, W sub n over 2. Yeah. W sub n squared is actually W sub n over 2. Yeah. Did it make sense? Yeah. Welcome. Let's see. Going backwards. Oh. So as I said, so this is where you are. So we are saying this is equal to this, and therefore, by definition of S1n or S1, whatever it is, it means this is actually S1k, S sub 1k, and Wn the power of k S sub 2k for k from 0 to n over 2 minus 1, because now these are shorter sequences. Yeah. Oh, yeah, 0 to n over 2 minus 1. Yeah, that should be it. Where this is simply this, where S1 of k is S1n, where S1n, when S1n is the even, these are the sequence of even samples, and S2n is a sequence of odd samples. Therefore, so what we are saying here is because of periodicity, we can have x of k, well, here we have put k n minus 2 for so that they can work better when it comes to what do you call it? Where is it? Yeah, we have put, there you go. Yeah, due to the periodicity, we can say x of k is s1 k minus n over 2. These are the other samples. You see, the first few samples, I mean, the first half, which now is the even. For the first half, we are going to use k, and then for the second half, we are going to use k minus n over 2. That is for n for the samples n over 2 to n minus 1. The first samples we are dealing with is from 0 to n over 2 minus 1. Yeah. I think it was here. Yes. 0 to n over 2 minus 1. And you are using periodicity and saying due to the periodicity, for the samples, now n over 2 to n minus 1, we can simply apply this. So for n over 8, this becomes x of k s1 of k plus w8 to the k s2 of k from 0 to 3. And then this becomes s1 of k minus 4. This is n over 2. That is from 4 to 7. And you can see what we are saying is it simply becomes like you are repeating the same thing. The only difference is what will be the difference is just your W8. You can see in this case, you are using W8 to the 0, W8 to the 1, W8 to the power of 2, W8 to the power of 3. That's the only thing that's changing, but this will basically be the same things. Yeah. Because this is 7, this is from 4. This means 4 minus 4. This is simply S1 of 0. And this, only the K is changing. And this one is S2 of K is equal to 4. That, of course, will be S2 of 0. So X of K, the next one, which will be the fifth sample, that will be simply S1 of 1. This one here. Yeah. S1 of 1. No. Okay. So sorry. This one here. S1 of 1 and 5. S2 of 1. For 6, is going to be 6 minus 4. So S1 of 2. This will be W to 6. And this is S2 of 2. So we are just having, so we are going to have now X1 to X4. And I hope you can see the difference. The difference with this is just the fact that what is changing is this. Everything else just repeated. Is that we are multiplying with the different WNs, different powers of WN. Starting with power to the power of 0 to the power of 1, just to the power of k. Yeah. So this just repeats itself. Yeah. The best way to look at it is because of periodicity. It's just you're just reproducing the samples again. I mean, you're just what do you call it? Try to get the best word. But this is demonstrated by using this formula. And here, this is supposed to be x of 3, not x of 4. Sorry, here. Change this. This x of 3. So it's supposed to be 0, 1, 2, 3. X of 4 is this one. So here we can do, here what we have done, we have separated the 8-point DFT to 4-point DFT. So this is we are getting the 8-point DFT by using 2 4-point DFTs. And what we are saying here is to get x of 0, you are going to have S1 of 0. This is called a butterfly diagram. It's called a butterfly diagram. And for this one, we are just doing the butterfly diagram specifically just for the first split. And although we look at it as, yeah, well, it's a split. But when you are doing the analysis, of course, you would start with combining two samples, then you combine 2 and 2, make 4, combine 2 and 2, make 4, then, so, but let's look at it from splitting, that you're having this, you're splitting now into this, and you're going backwards. But when you draw the butterfly diagram, you'll always be starting with the input. So you'll be starting with 2 inputs, another 2 inputs combined into making 1. Yeah, but let's see. But that's why we are approaching it from this side, from the output side, because it's what, just to show how the split is done. But eventually, you're going to see how our butterfly diagram looks like. So here we are saying x of 0 is S1 of 0 plus S2 of 0 multiplied with this factor, W8 to the 0. Yeah. I'm trying to go backwards. I think going backwards is this way. Yeah. That's what we are saying here. X of 0 is S1 of 0 plus W to the 8, the power of 0, S2 of 0. Yeah. X2 of 1 is simply S1 of 1. That is, oh, sorry, X2 is S1 of 1 added to S2 of 1. That is from the even and from the odd. Yeah. And then multiply with W to the 8. I mean, W sub 8 to the power of 1. Then, and so on and so on and so forth. So you can see, I think that one you can understand. And when you reach here, we are saying this is S2 of 1. Why is this? X of 4. X of 4 we are saying is S1 of 0 and plus S2 of 0, but now you're multiplying with a different W8 of 4. So actually this W8 of 4, sorry, the way I've drawn it may be confusing, does not apply to this. You can see we have put 1, 1, 1, 1. It means this is just, it's not multiplied by any factor. S1 of 0 is just multiplied by 1, and then it's added with this multiplied by W8 to the 4. So this W to the 4 refers to here. W8 to the power 5 refers to here. W8 to the power 6 refers to here. And W8 to the power 7 refers to here. So you can see X4 to X7 is simply adding this to this, but just multiplying with the different powers of Wn. So I think this is clear. But of course, you can notice one thing is that this is 0. I'm trying to see whether it comes out at this juncture. Yeah, because what we have we change the bits. We do some what we call bit reversal. Yeah. By bit reversal, we mean if we represent these numbers 1 to 7, 0 to 7 as binary bits, this will be 0, 0, 0. This will be 0, 1, 0. This will be 1. Well, I think we start with the positions. Let's consider this to be position 0, 1, 2, 3. We are saying position 0. God, when you can't write, it's so difficult. So the position 0, n is equal to 0. You're not going to start with x of 0, x of 1, x of 2, x of 3. What we are doing from that, we are saying that well, yeah, it's okay, because they are no, I think we might not look at bit reversal at this point, because what bit reversal means is x, the first position will still be x of 0, because even when 0, you don't reverse 0, 0 will just remain 0. But the first position, which is 1, 0, 0, if you reverse, no, 0, 0, 1, if you reverse that becomes 1, 0, 0. So it means this first position would have the fourth sample. Yeah, but that does not come out here. That would come out after we do the next decimation. Yeah, once we do the next decimation, that's where it will come out. Yeah, this is where you're going to get the bit reversed order. Yeah, this is the bit reversed order. That's what I was trying to explain. I think it doesn't come at this point. Sorry about that. So I'm going up back. It doesn't come at this point. But later we are going to see at the input, the order is reversed. It means in this first position, of course, n is equal to 0. So you are going to have x of 0, because 0 does not change even when you reverse the bits. The second position, we are going to have, which means the input to this, we are going to be the second position, which is now the input to the first n over 4 point DFT. We are going to have 0, 1, 0, 0, 1, which is 1, reversed, becomes 1, 0, 0, so it becomes the fourth sample. And here we have this will be the second. This is first position. I mean, this is first. This is second. So second 0, 1, 0 does not change. It still remains 0, 1, 0 when you reverse the bit. So that is x over, that is x of 2. This is the third position, which is 0, 1, 1. If you reverse the bit, becomes 1, 1, 0. So that will be x of 6. This is the fourth. Yeah, this is the fourth. 0, 1, 2, 3, 4. Fourth here, we are going to have 1, 0, 0 becoming 0, 0, 1. So that is x1. Yeah. You must arrange them in that bit reversed order so that these ones will come out in this order. Yeah. If you put these bits into this in the correct order, that is, you get 0, and then of course you are combining with the even one, with the next even one, which is x of 2. This order will not be maintained. Yeah. So if you want to maintain this, the order of this sequence, then this is how you are going to input them at the at the beginning. Yeah. Because that's what we are talking about. We are saying by decimation, it means we are getting all those samples and picking 2 samples at a time, and then the 2 we make them into this one, and these 2 into this one. Then this one's combined to make this one. Yeah. So this from the time domain to the frequency domain. Yeah. Let's go back to where we were. I think we were here. Yeah. So that is the first decimation, 8 DFT to 4 point DFTs. Yeah. Are we good so far? I know it's a bit difficult when I can't write, both for me and for you. So I'm explaining purely from, it's a bit difficult when you can't write. But I hope everybody is following. Ngesa. You're following?
Yes.
Very good. Very good. Then we can move on. Yeah, what we have done here, we are saying that you can separate the 4 point DFT to 2 point DFTs. And that's what we are doing here. Now here we have used, you can see from our drawing here, we have used A, B, C, D. Yeah. Instead of calling S1, S2, so A, B, C, D. So you're combining, you can see you're combining to get, now to get here. I think what you I want to, so you are what you are getting here is S0. You want to get S of 0, no, S1 of 0, sorry. S1 of 0, S1 of 1, S1 of 2, S1 of 3, and this is S2 of 0, S2 of 1, S2 of 2, S2 of 3. So you can see how we are combining those from here. We're using the same thing. We are seeing from 0 to n over 4 minus 1. Now we have divided this n over 4 minus 1. You are going to use this formula here, and therefore, since these are periodic, we are saying S1 of k for k, A of k minus n of 4. This is going to apply for the samples n over 4 to n over 2 minus 1. You see, before we are going from n over 2 to n minus 1. Here we are going n over 4 to n over 2 minus 1. Yeah, because now we have a few samples. So for n over 8, this will apply, and that will give us this. You can see what is S1 of 0 and to S of 3, it has got A and B, and S2 of 0 to S2 of 3 has got C and D. From here you can see C and D. So this is S2 of 0, S2 of 3, and this S1 of 0 to S1 of 3. Yeah. And then this is what we had done. Oh, this is the And then, of course, this is how we are combining to get that. It is here. So this is this. And now these are these two, the ones we have done last. So there's a full implementation. And what we are doing here is, of course, now for this input, that one is straightforward, because here you can see you are moving from here to here. These are the output of N2s. These are outputs of A, B, C, D, and these are the outputs of A combined with B, and B combined with, and C combined with D, and then here the S1s, S1 combined with S2. You get that. Yeah. Here you can actually work it out directly from just definition of. I think, let me see, where will I go from the beginning? That's the end. Just from the definition of FFT. Here, definition of f of t, if you have got S of k, x of k, where n is equal to 2, if n is equal to 2, then you only go S of k from 0 to 1. Excellent. To this, if you work it out for just samples, let's see. Somebody's coming in. It's a shame I can't work it out here. But what you're saying, if you work it out, you're going to find that, where were we? You're going to find that to get x1, because there are two. You see, there are only two samples. But we are inputting sample 0, the 0th sample, and the 4th sample. But if you put it as just two samples, you are going to see that the output here will simply be x of 0 plus x of 4, and this one, I mean here I mean the capital X, that is the DFT, where x of 0, that's the x of k, x of 0, just this plus this, and x of 1, which is the other sample, of course here it is x of 4, for the reasons I explained. To get this order, you cannot put 0 and 1, but I'm just looking at it as this was just inputting 0 and 1. So this will be x of 0 minus x of 4. Yeah, which is minus x of 1. I'm considering two samples. I hope I'm not getting confused by from 4 to 1. But I'm saying for each case, you can just look at this as two samples, as 0 and x of 1. And then if you work it out directly from the definition, you're going to find out that the output is this. I think that comes from the fact that e to the minus j pi, j2 pi, j2 pi, of course n is equal to 2, so it is e to the j pi is actually minus 1. You can work that out. Yeah, because I hope everybody got me there. If you work out for only two samples, it means n is equal to 2. So W, of course it is here. Why am I even going very far? I think it should be one of these. Let's see what that is. It should be this one. W4 to the power of 2, W2 to the power. I'm trying to see why I'm getting -1. It should be, I think this, that WN, W2 to the power of 1 should be -1 also. Yeah. But you can work it out. It's easy. Just use Euler's formula so that you have cos minus j pi. No, cos minus pi plus j no, there's no j pi, sorry. It's simply cos minus pi plus j sine minus pi. Okay. You don't realize how important writing is. It organizes your thoughts. So that is what we are going to get finally, and you can see the bit reversed order is applicable here, and that will be the output. And we have given the values here. W4 to the 0 is equal to W8 to the 0. Of course, anything to the 0 is 1. W4. Of course, here we have used, you can see we are using W4 to the 0, W4 to the 1. We could as well have used W8. But if you use W8, then this would have been W8 to the 0. This will be different W8s. The powers will just be different. But here we have used W4. See in our diagram here we have used still W8. But you can still convert them to W4s. Because when you're dealing with this particular case, you're actually dealing with W4s and other W4s. But you can also look at them as W8. Yeah. And it will give you the same thing. Actually, that one is given very clearly here. W4 to the power of 2 is just the W8 to the power of 4. The same thing. W4 to the power of 3, that's W8 to the power of 8, to the power of 6. Yeah. So the only thing is, if you look at them as W8, then that will be actually that's how the periodicity is coming in. Yeah. So now let's see how this algorithm works, or reduces the complexity, because that is what is of importance to us. So you are split then DFT to 2 n over 2 DFTs. Then you split the 2 n over 2 DFTs to 2 n over 4 DFTs. Keep splitting up to r times, where r is log 2n. So these are the splits up to that. Each DFT requires n over 2 squared plus and 2 on n complex multipliers. So how we check it? The first split, you require 2 n over 2 squared plus n. Yeah, you see. So whenever you do n over 2, add the n of that. So if it was, so the first one, of course, is n over 2 plus n. So whenever you split, it goes to plus n complex multiplies. So we are saying the first split gives us that 2 of this plus n. Second split gives us 2 of this plus n. Yeah, I hope you're able to see that. And of course, you still have the other n. Yeah, plus n plus that other n. Then that becomes, if you work this out, again, I can't write, so you can do it by yourself. So from here, you're going to see that this simply becomes n squared over 4 plus 2n. Yeah. Then where the second n is coming from is because of this 2 to the, you see this 2 applies to also n over 2. That brings another n. Because it is this plus now the 2 of those split again, so it becomes n over 2. So you get the 2n. You do the large split. This n over 8, this requires 2 into that plus n. You see, whenever you have n over 2, you have n complex multiplies. Yeah. So that becomes that, and that produces another. You see, there is this 2, and there is this 2, and there is n over 4. So it will produce another n. So you're going to get 2. Remember, this 2 is the first 2. You're not interfering with this one. So the 2 will give another n. So you get plus 3n. So if you do the R split, you're going to get n over 2. You can see you're always getting n over 2 divided by 2n. So it is n over 2 to the r times rn. Yeah. So that is plus rn. That is this plus this. So if you go splitting, you can see, obviously you can see that from the first split, second split, you can see that the R split would give you that when adding 1n. Now, this is simply, of course, R, the split, R is log 2n. Yeah. R is log 2n. So this will become n squared R. Okay, I think just look at it. N is, of course, it's the same thing. It means n is equal to 2 to the r. Yeah, n is equal to 2 to the r. So this becomes simply n squared over n plus. So if n is equal to 2 to the r, it means r is log 2n. Yeah. So this becomes log 2n, and this becomes n. So when n is large, the term that becomes large is this one. So this one, yeah, this is simply n, but this is log 2n. So we look at the bigger complexity, which is n log 2n. That's what we're doing. It's approximately this. We are ignoring n and looking at n log 2n. So we are moving from n squared to n log 2n. Does everybody appreciate how we got reduced complexity? Yeah. So it looks like everybody is okay with that. Here you are given an example. You're given 1, 1, 1, 1, 1, 1. I mean, I just made it easier. Just use, so you don't have a lot of multiplications, complex multiplications. So I just used a sequence of 8 ones. So you are told to find out the DFT using DIT, FFT, or 8-point DFT matrix. Of course, you can work with 8-point DFT matrix. I didn't work it out, but that is the 8-point DFT. You can see it has a lot of this 1 plus j divided by a square root of 2. That is the 8-point matrix. You can do it as exercise. You can try to work this out using 8-point DFT matrix. You see what you get. Let's look at it using DIT, FFT. So these are your inputs. Luckily, your inputs are 1, so just 1, 1, 1, 1, 1. So here you're adding 1. So to get this, you add 1 plus 1, you get 2, because this is just, you are just adding this. When there is nothing written, it means you're just multiplying by 1. Yeah, it's just a weight of 1, so this is 1, and this has a weight of 1, so it becomes 2. This becomes 1, but this is weighted by -1. So this is 1 times -1 is -1. So this is 1 minus 1 is 0. And since all our samples are just 1, 1, of course, that's what's going to happen at every point here. Yeah. So I think we understand the first step. The second step, we are going from, so this is 2, and here you have got 2, and W4 to the power of 0 is 1. So 2 is simply being multiplied by 1, and this is 2 multiplied by 1. So that is 4. The second one, we are using, yes? Did somebody ask a question? This second one here, we are simply adding this 0, this is just 0, and this is 0, whatever you multiply with, it means 0. So this, you're going to see that this is going to be everything. Oh, here, up here it will be just 0, 0, 0, yeah? Because you have zeros, you're adding, it's only the first one which you have a value. Oh, no, here we are adding what? Here we are adding 2, and this 2 is multiplied by -1. This W4 of 2 refers to this line here. So that is equal to -1. So 2 times -1 is -2. 2 plus -1 is 0. This one, again, this is 0 plus 0. Yeah, that's okay. Here the same way, this is 2 plus 2 times 1 is 4. This one is 0 times, this applies to this, to the 4 minus 1. This, oh, sorry. These ones apply to this, but these ones apply to this. There's some confusion there. This apply to this, and this apply to this. This apply to this, this apply to this, yeah? So it will be this, which is just 2, or it will be the same thing, 2 2 times minus 1, that is 0. So it will just be like here, up here. So it will be 4000 and this 4000. And then eventually this will be 4 plus the 4. Others will be 4 times plus 4 times minus 1, which is 0. And everything else will be 0. Yeah, you can see why this one will be. Let's get where there is a 4. There's a 4 here, so that is, you can see why it is getting 0. Yeah, it's because of that, and that applies to here also, where you are picking, what. So you get an 8. So everything else is 0. So if you have the DFT of that is simply 8. Yeah, 8 and all zeros. You can try to do that. You can see how simple it is using the algorithm. Yeah. Now try to do that with the 8-point DFT matrix. It's going to be a lot of work. Do you have any questions? Sorry, we have moved too fast because I was not able to elaborate a few of the things. But I think it's very clear in the notes. You can go and look at them again. And I'm sure you'll be able to. So I think what you can do is just send to the chat your number, and we meet at 3:30 in the evening. Have a good day.